Hello everyone and welcome to our next episode from Java Collections series. In this episode we are going to discuss about sets. But before we do that, if you find the content of our channel helpful, please give us a like and subscribe. So, what is set? Set is a data structure that stores items, like many different data structures. But its main advantage is that it does not allow duplicate items. For example, let's say you are going to buy some ingredients to bake a cookie and you need flour, sugar, eggs and butter. But you only need to buy each ingredient only once, so you do not need any duplicate purchases. You should just buy flour and then scratch it out from your list and move on. This can be one of the real-time example why you could use set. One of the popular implementations of set is HashSet. And HashSet is using hashmap to store elements by using hash code and equals methods. We have not yet discussed in our Java Collections series how map is working, it will be in the upcoming videos, but for this episode we will just mention general ideas of how it is working. Inside hashmap we have entries and each entry has key value pair. So when we are storing something inside HashSet, such as for example flour or sugar, it will be used in underlying hashmap as a key, and value will be some kind of dummy object. And to represent it with this picture, you can visualize it as keys will be, for example, butter, eggs, flour, sugar, and values will be dummy objects. And in Java implementations, it is called present. In terms of time complexity, adding an element and also checking if the element is in HashSet will take O of 1, constant time. And this will be on average. And in some situations maybe this time complexity will degrade to O log n, and reason why it could happen depends on the analysis of how the hash map how the map internally works in Java. So we will explain it in our upcoming video when we deeply discuss how the map is working. But for the purpose of this episode, it is enough to remember that most of the times, in most cases, adding an element and also checking if it exists will take constant time. Another popular implementation of set is TreeSet, and we are using TreeSet when we need sorted items. So, for our example, if we need to sort the ingredients by their first letters, natural ordering will be that B will be before E and S will be after E, because that's how alphabetically these items, these letters are arranged. But in general, whenever we need sorting of the items inside set, we should go for TreeSet. In terms of time complexity, adding an element in TreeSet will be O log n, and also finding an element will be O log n. We will analyze why it is log n and not just n, but before we do that, we should mention that TreeSet is using balanced binary tree. Before we explain it, we should mention what is unbalanced binary tree. So, unbalanced binary tree looks like this. We have these elements, and each element has nodes, right node and left node, and right node, child node, will be more than this root, and left will be less in value than the root node. But in this situation we can see that we have these nodes which are much higher in value than previous nodes, and there are no left nodes, and there are orphans. So this represents unbalanced tree. But in case of balanced tree, we can see that we have this root element 26, and everything on the right side will be more than 26, anything on the left side will be less than 26. And this happens on each level of this tree. Even for 14, because 20 is on the right side of 14 and 10 is left side of 14. So in general it will be at each level, this logic will hold, and there will not be as many orphans as in case of unbalanced tree. So to connect this balanced binary tree with log n, we should analyze, for example, concrete situation. Let's say we are searching 44 and start at 26 and we make comparison. 44 is more than 26. So we are automatically ignoring all the left side, all these left elements. Why? Because we know that in balanced binary tree, all left side elements will be less than 44, 26, and since we are searching for 44, we would never go on the left side. So what happens is that instead of n elements, our search will be just halved down to n over 2, and it happens at each stage. For example, at 38, we compare 38 to 44, and 44 is more than 38, so we will never go on the left side, and this 32 will be just eliminated. So it happens on each level of the search, and because of this we are deriving log n time complexity. And if you need mathematical analysis, we can generalize this logic. So at level 0 root there is one node, level 1 has 2 nodes, at level 2 there are 4 nodes, and to generalize, at level h there will be 2 in the h power of nodes. Then we should create this formula for total number of nodes, and it forms this progression. And this progression can be solved, and first we derive n and then we derive h. H is the height of the binary tree, and based on our previous analysis of big O notation, we know that we should ignore from this equation the constant values. We can conclude that h, height of the tree, grows logarithmically with n. And this is why we say that this is function of log n, and it is not just O of n. If it was O of n, it would be relatively slower than this one, because there will be n elements to go, so it is much faster, but of course log n will be slower than constant time, because constant time is getting the element right away with single step, and in this case it is not single step, we still have to do some searching. Another popular implementation is LinkedHashSet, and we should go for it when we need to maintain insertion and access order. It allows one null element like HashSet. There is memory overhead, slight memory overhead, because it uses doubly linked list, and also performance will be slightly slower than HashSet. But unless we need insertion and access order, we should just stick with using HashSet. To summarize what we've said in this video, sets do not allow duplicates, and this is the main reason why we would use them, this data structure. And HashSet is a go-to implementation unless you need something special. If you need sorting, then you should use TreeSet. If you need order of insertion and access, then you should use LinkedHashSet. And of course, like we mentioned, different time complexities are available for different implementations. And again, the choice which implementation to use depends on your use case and what you are trying to achieve. So this was all about sets. In the upcoming videos we are going to discuss how the map data structure is working. Stay tuned, thanks for watching, and I'll see you in the next one.